This may seem like a strange lecture to include in a 21st century electromagnetics class because it's really not electromagnetic. We're just learning how to interface MATLAB with CAD tools. So far in this semester, you've seen a lot of the electromagnetic stuff, and I think you have the feeling that some of these structures can become very, very geometrically complex, particularly when we start off with a complex unit cell, spatially vary it, combine it with other things, and it just turns out the CAD tools are not in place to generate these types of geometries. Now we can generate them in MATLAB, and then we're left with this interface between MATLAB and CAD. And I found this to be a pretty strong choke point, and I think it's worth discussing in this class. Here is the outline of the lecture. The first thing we need to do is talk about text files in MATLAB, how to open them, how to close them, how to read lines of text from text files, and how to write lines of text to text files. Given that, it makes sense we also need to talk about string manipulation in MATLAB. How do we take a string that we've read from a file and parse different pieces of information from it? And likewise, how do we take different pieces of information and compile it into a text string that we can then write to MATLAB? Given that background, we're ready to talk about STL files, which is the standard file format for describing 3D objects in 3D printing. It's a limited file format, and it will change, I think, over the coming years, but right now that's the standard for exchanging 3D geometries and driving 3D printers. So what we want to talk about is STL files in general, and then how do we read and create STL files from MATLAB. I'm going to talk you through creating ASCII STL files, text STL files. They become very large for complex objects. A binary STL file is much more compact and not a whole lot different than what we're talking about here, but I didn't want to get into the binary commands from MATLAB. So a text file STL is just fine for this lecture. Given that, I want to talk about surface meshes in MATLAB, how to visualize them, how to generate them. And then we're ready to actually create an object on a grid, generate a surface mesh, and then save it as an STL file. Maybe we want to do this the other way around. Maybe we read in a surface mesh and we need to build a 3D object on a 3D grid, maybe even a 2D object. And then I'll finish discussing a little bit about point clouds, and then another trick that I've come across in importing custom polygons into SolidWorks. Okay, on to text files. No matter what we do with a text file, the first thing we always do is open it, and in the case if it doesn't exist, we're creating that file, and then the very last thing we do is close it. Now MATLAB can behave very strangely if we don't close it and then run the file again, because now it's trying to open a file that was never closed. Can't really blame this on MATLAB, but we always have to close that file. And if we're in the middle of creating a file and it errors out, you probably at the command prompt want to manually close the file. So the two big commands here are fopen and fclose. So fopen opens a file. Here we have the name of the file. If it doesn't exist, it will create that file. And then we give it an input argument. Right now I have it as R. R means it's read only. If we only want to read the file, that makes it very safe. We're not going to mess up the file in any way or corrupt it. If we wanted to create a file and write to it, this would be a W. Now for opening a file, it gives back a file ID that we would use to access that file while it's open. It turns out if that's a -1, that means it's not a file ID because that should be a positive number, and we might want to error out saying, hey, we can't open the file. Then we do all the stuff. Maybe we're writing to the file, maybe we're reading from it, but at the very end, we close it. And that's very important to close it. If your program crashes in the middle of writing a file or reading a file, manually close it at the end. So suppose a file is open, we're reading it. How do we read a line of text? Well, a good command is the fgetL, or file get line. We just hand it the file ID, and it will read the next line of text. If we repeated that command, it would then read the one following, and so on. So for example, we could write a very simple while loop that would read and display all the lines of text in a text file. So while we are not at the end of the file, do this. Read a line, display the line, and it keeps doing that until it reaches the end of the file. Well, now we can also write a line of text to a file. So let's say this file is already open and we have its file ID. We would use the command fprintf, give it the file ID, and then the second input argument is the text string that we want to write. In this case, we're writing solid pyramid. Notice these two symbols afterwards. What this is happening, this is a carriage return and a line feed. So in other words, we're going to the next line. So if we repeated this and we opened up the text file, we would see solid pyramid, next line, solid pyramid. Without that, you would just see solid pyramid going across one horizontal line. We can also write numbers to the file. We're doing the same basic thing up here, where when we finally write, we're going to give it a file ID. However, we'll give it a text string, and we'll give it some ANSI standard notation here for including numbers, and then we give it a list of numbers. So let's say these are the numbers, and our text string will be facet normal, and we'll discuss what that is later. This is actually part of an STL file. But this says we want to display a floating point number. We want the field to be a total of 8 digits, and we want 6 digits of precision. And evidently I'm keeping that same format for all 3 numbers, and then a carriage return line feed. So when we do that, it writes facet normal with 3 numbers, and it writes that to the file. Just a summary of the ANSI formatting. Recall we had a carriage return and then a line feed or new line. And so this slide is just a summary of the different notation, but what I've displayed on the last slide is about all you'll need to know for this work. But there certainly is more we can do. Integers, etc. Here's more summary of conversions if you want to display hexadecimal, etc. And then finally, flags. On to string manipulation in MATLAB. Parsing strings. This is when maybe we've read a line of text from a text file, and it contains different pieces of information, and we want to pull those out. So we can use the command scanf to do that. So for example, let's say we create a string, or maybe we've read this string from a text file. It says hello class. We can pull the space out of that. We know this will pull off the first word, it will skip the space, and it'll pull off the second word. So T will come out being hello class. If we use the same text string, but we put a star in there, that says skip the first word, ignore the space, and grab the second word. So T comes out being just class. So in fact, if we know how many words there are in a line, we can arbitrarily skip whichever we want to. For example, maybe we want to pull off 2 numbers from this sentence. And one thing, the sentence will always have to read the same way, but with different numbers here and here. So what we want to do is skip the first 2 words, so %*s, and then we're going to grab a number, %f. Then we'll skip 3 words, %*s, and grab a second number. And then we'll skip the second 2, although we probably don't have to do that. And we come out n being an array of numbers, and it'll be 25 and 6. We've pulled off these 2 numbers. Maybe we have a string or a series of text strings, and we want to pull off certain words or compare, etc. So there's a very neat command in MATLAB, strcompare, string compare is what that means, strcmp. So let's say now we have 2 strings, cat and dog, and we want to compare them. Well, cat and dog are not the same, so C comes out being 0. Our comparison is false. What if we compared cat and cat, but we capitalize one of the C's? Otherwise it's the same word. Well, if we compare it, it still is not the same. So this is a case-sensitive command. Finally, if our 2 strings are cat, and we compare them, we get a 1. So strcmp compares 2 strings, and it is case-sensitive. Then there's another command, strcmpi. let's see what happens here. We compare cat and dog, we still get a 0. Now we compare cat to cat, and there's a case difference here, but here they're saying they compare. So the I means insensitive. We're comparing strings, but it's case insensitive. And of course, if we compare cat to cat with all the same case, we still get 1s. And the last one, str find. If we want to find a particular word in a sentence, or know if it's there, and also know where it occurs, we can use this string find command. So let's say our sentence that we've read from a file is University of Texas at El Paso. We want to find where Hawaii is in that. So we do str find, and it comes out with the index, the array index of where that is. Well, it doesn't find it, so that array index is empty. Well, maybe we want to find where the word Texas is in this string, University of Texas at El Paso. So we do the str find, and it comes out with the number 15. So the fact that this is not an empty means there is that word in there, and that tells us where that word occurs. So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So Texas begins at the array index of 15. Very often we need to convert between numbers and strings. And so we can go from a string to a number. So maybe this is a number we've read from a file. We want to convert it to an actual number. str to num, string to number. So we hand it the string, and out comes a number, 534. Also, it takes this exponential type notation, and string to num, and out comes a number with an exponent. And we can go the other way around too. We can start with a number and convert that to a string. So now we'll have a string 1, 2, 3, 4. We can make it decimals, that'll have that. We can also format it. We have 1.2345678 but we only want 6 digits of precision, then we can set that format. We'll only have 6 digits of precision. So these are all strings that came from numbers. Okay, so now we are masters of text files and manipulating strings in MATLAB. On to STL files that we will read and save as ASCII STL files, or text STL files. So what is an STL file? It stands for Standard Tessellation Language. We have some 3D object. Imagine meshing its surface with a bunch of triangles. The STL file is simply a list of those triangles, nothing more. Now, some programs store information in STL file a little bit differently so that they can store things like color or texture or materials. This is non-standard. In my opinion, it's a little bit dangerous, and I don't recommend doing that, but I want you to be cautious about it. Also, the last thing, we'll be doing text files because I think that's the easiest and most intuitive to understand, but it's definitely not the smallest file size. The binary files will be much smaller. So what is a surface mesh? Let's say we have a sphere, and the reality is this sphere is a solid object, or should be. But if we do a surface mesh, it's just triangles on the surface. So really, we can't tell just from the surface mesh whether that object is actually filled or not. We assume it is, and for 3D printing we definitely assume it is, but the STL file is just a surface mesh. Here's the format, really all just in one slide here. So it starts off with solid, and then you're free to give it whatever name. Then it's really just a whole bunch of repeats of this section of code. So this is how we tell it one of the triangles, and this section of code repeats for every triangle that there is. And at the very end we say end solid with the same name that we started with, and that's it. So let's think about the information for each triangle. Over here I'm drawing a triangle, and this follows something called the right-hand rule. If we take our right hand and we curl our fingers around those points going counterclockwise, then the surface normal points in this direction. And so we want to order these points so that this facet normal points to the outside of our device. So the inside of our device, where the material would be on this side. This would point outward and away from the device. That's the convention. So for each triangle, we say facet normal, and then we give it the three components of the normal vector. And this is following the right-hand rule from the vertices. Then we say outer loop. Then we give it the three vertices. We just say vertex. Then the three components of the first vertex. Vertex, the three components of the second vertex. Vertex, and the three components of the third vertex. Then end loop, end facet. This section repeats for every single triangle in our mesh. And that is it. That is all is in an STL file. Now, one thing I want to point out, if we list these in the order of the right-hand rule, we can calculate the facet normal from it. So in a way, there's redundant information here. And a lot of programs recognize that. So if the vertices are listed in order, we can calculate the facet normal from that. So under the heading facet normal, that's where sometimes folks will put color or some kind of surface property or who knows. So when we're reading STL files, we want to be cautious of that when we read a facet normal, that may not have the same meaning that we think it does. But in the standard STL file, that is the facet normal. Here's an example STL file. And the entire STL file is here. So I went into a program called SolidWorks. I created a simple triangular pyramid. So this only has 4 sides, and saved it as an STL file and called it pyramid. So solid pyramid. Notice this section of code, which saves as a triangle, is repeated 4 different times, and then end facet and pyramid. So here's the normal for the first facet, and it's 3 vertices. The second triangle, the second normal, facet normal, and it's 3 vertices. Third triangle, the normal to it, and it's 3 vertices, and so on. And we just have a 4th one. So that is an entire, complete, correct STL file for that 4-sided pyramid. Now clearly, the more complex our surface is, the more triangles that will take, and we can have some very, very large text files. Let's think about a single triangle. Just to repeat some concepts here, we put them in order of the right-hand rule. So we start at vertex 1, and we go counterclockwise to vertex 2, vertex 3, and back to vertex 1. So we curl on our right hand, our fingers in this direction, and our thumb will point on the facet normal. So it has to follow the right-hand rule. Now, some programs also, because it's a little bit redundant, if we list the vertices in the order of the right-hand rule, they'll just set the facet normal to 0, 0, 0 and never bother calculating it. So again, the theme is, don't depend on the information under facet normal to really be the facet normal. Also notice that if we have adjacent triangles, for example, there's this other triangle over here. This shares 2 vertices with facet number 1. Another thing I want to point out, that in this description of triangles, it seems as if we're set up to handle arbitrary polygons. Like, what if we listed 4 vertices? Wouldn't that describe a square? Maybe, and I think some readers can do that, but don't do that. So we are only going to use triangles. That's the standard, and if we follow that, then any program will be able to read your STL files. And I'll warn you one last time about facet normals. It's a little bit redundant information, so a lot of times that contains other things, like shading, color, etc. And if they do include the facet normal, then sometimes the vertices aren't listed in the order of the right-hand rule. So there's a lot of bad news here. I'm telling you, don't depend on anything And that's absolutely true. It's very difficult to read STL files. Even if we buy commercial software, sometimes we save an STL file from one and another one can't read it. And it's all because of these little things. But if you follow the rules, I would always put the facet normal in the facet normal, and I would always list the vertices following the right-hand rule, and then everything should be able to read your files. Let's talk about now about actually reading and writing STL files in MATLAB. Here's how MATLAB likes to store the data. If we have n facets, big N facets, in other words, we have big N triangles, then that means we have less than or equal to 3 big N vertices. That's because they're going to share common vertices. If they were all completely separate, we would have exactly 3n, but that wouldn't make any sense. They're connected, they share common vertices, so it has to be less than or equal to 3n. I wouldn't even say it's equal to, I'd have to say it's less than 3n. And we store two things. We store all of the facets and all of the vertices. So we don't know how many vertices because just given here, we don't know how many points are shared between different facets. But we know we have n facets, and they have 3 points each in each facet. For each vertex, we don't know how many vertices there are, but we know that there's 3 components to each one. So we really have two-dimensional arrays. One of them containing the triangle facets, and the other one containing the triangle vertices. Let's think about this array of vertices. There's a lazy way to do this. So we start off here with our pyramid. Notice it has 1, 2, 3, 4 vertices and 4 sides. We could just pull off the 4 different sides and make all the vertices unique numbers. So we'll call this vertex 1, vertex 2, vertex 3, moving to the next triangle. Even though reality this is vertex 2, these 2 points are the same thing, and also these 2 points are the same thing, we can just call it a different vertex, and this works perfectly fine. The redundancy will just lead to a larger file size. So doing this very lazy, we just give each triangle its own vertex, and we create an array. And in the columns are, we go 1, 2, 3, however many vertices we have. Here it's big M vertices. Working across in the row, we have the X, Y, and Z component for the first vertex, X, Y, Z component for the second vertex, and so on. So this would be a lazy way of storing the vertices. Now, let's recognize the redundancy. What we called in the last slide vertices 2, 5, and 8 really are the same vertices. What we called 1, 6, and 12 in the previous slide are all the same vertices. What we called 3, 7, and 10 were all the same vertices. And what we called 4, 9, and 11 were all the same vertices. So using 12 total vertices, we would have 12 rows in this matrix. So imagine a much larger structure that has millions of triangles. We would have many millions of vertices. Instead, we really can compress this down to just 4 points. So we'll have 3 columns and 4 rows in this V array. So here's what that would look like. Recognizing that there are common vertices. Notice again, this is the same point, and now we convey that for the second vertex. Likewise, this is the first vertex. So this is a much more intelligent way. It's a much more compact array of vertices. I would say that's the best way to do it. I know in SolidWorks, when you save an STL file, it doesn't do it. It does the lazy way. Not really a problem with that, but the file size can be smaller. And probably if you're manipulating that STL file, it might be a little bit faster if you had a more compact array of vertices. Now let's think about the array of faces. The array of vertices actually had positions. So those numbers could be 1, 2, 3, 4, very complex. In the array of faces, we're not talking about positions anymore. There's all integers in here, and we're referring to the indices of the vertices. So for example, the first row in this array F are the indices of the vertices of the first triangle. So here's the first triangle, and notice it has vertices 1, 2, and 3. And so we include 1, 2, and 3. This triangle has vertices 5, 4, and 6. And so it would contain a 5, a 4, and a 6 if this were the second triangle. And so on. So for every face, we have a row, and then working across that row, it's the indices of the vertex. And what does the indices go back to that V array. It's which row in that V array gives you the positions of those vertices. So here's an example of the actual numbers. Let's say we have this pyramid again and we're being lazy. Here's the list of all of our vertices. And there's redundancy here because we know we really only have 4 points, but we're listing 12 here. Well, if we look at the first face, we would say that has vertices 1, 2, and 3. So we would go down here to rows 1, 2, and 3, and then we have the positions of those 3 vertices. We'd go to the second face, 4, 5, and 6, and now we come down, 4, 5, and 6. These are the positions of the vertices in the second facet, and so on. The third facet, 7, 8, 9, and so 7, 8, 9. And the last one, 10, 11, 12, and 10, 11, and 12. Well, if we had a compact array of vertices, things look a little bit different. We know we only have 4 points in our pyramid, so we only have 4 points stored in our V array. And our first face is still 1, 2, 3, but our second face now is 4, 2, 1. So if we were to go down here, it's talking about this fourth point, and then this second point, and then this first point. So both the lazy way and the compact way work. This leads to smaller file sizes, but both work just fine. SolidWorks, in fact, creates the lazy array. Okay, now how do we read an STL file into MATLAB? And we know that there's things that we have to skip. We're expecting them. Things like facet normal, outer loop, vertex. Words we know that'll be there, but we can skip. And we know how to do that from earlier in this lecture. So step 1, we'll open the file as read-only. We don't want to open it as a write file. Technically, we could read it then, but we also stand a chance of messing it up. So we open it as read-only. We read the first line and store the object name if needed. Remember, that was the name of the file, but in my codes, I just skip that. Then we go ahead and read all of the facet data. This is this group of text that repeats for every triangle. So read the facet normal, and we can read the integers that follow that. You can throw them out, you can use them, that's up to you. Then we have the next line that'll say outer loop. We'll just skip that line. Then we go ahead and we read the vertex line. It'll be vertex and then 3 numbers following. And so from previous slides in this lecture, we know how to pull off those numbers. So we'll have the numbers for vertex 1. Then we read vertex 2. Then we read vertex 3. Then we'll skip the line that says end loop. We'll skip the line that says end facet. We've just read in 3 vertices. We'll add those vertices to our V array. And we also just added 1 facet. We will add the facet to the F array. Then, if another facet exists, we go back and we do this. So we just keep repeating and repeating and repeating and repeating. Finally, at the end, it'll say end solid. We'll just skip that line. And then we close the file. And then if we want to, because we potentially had redundant vertices, we could choose to eliminate those. Maybe we're even smart enough while we were reading them to figure out if they were redundant and eliminate them in real time. Either way works. What about writing an STL file? Very similar to what we just did, except instead of reading lines, we're compiling strings and writing it to a file. So we'll open a new text file, and the very first line will say solid, followed by the name of whatever that is. We used pyramid earlier. Then we set up a loop, and we loop through all of the facets in our surface mesh. For each facet, we want to go to our vertex array and grab the vertices so we know where they are. Then we'll calculate the facet normal. We could do a number of things. We could follow a right-hand rule. We'll talk a little bit more on the next slide of how we reconcile that if we created a surface mesh from a 3D array. But somehow we have to calculate this facet normal and make sure that the order of our vertices is following the right-hand rule. Then we write our line facet normal and give it the 3 components of the surface normal. Next line we write outer loop. Next line we write vertex 1 followed by the 3 components of that vertex. Then vertex 2 and vertex 3. Remember, put these in the order of the right-hand rule. Then the next line we write end loop. Next line we write end facet. And we repeat this for every single facet, every single triangle in our surface mesh. When we're done, then we just say end solid with the name. And that was the same name that we put up at the beginning. Then we close the file and we're done. Back to this reconciliation of the surface normal. One thing that's common just due to how we do things in MATLAB for our models, we'll build objects on a grid. So here's some strange looking object on a grid. Then we can calculate its surface mesh, and later in this lecture I'll show you how to do that. To take from a grid that has all zeros and ones where there is or is not material, we can mesh that surface. But this little red line is tracing the perimeter of that surface. And what we want to do is figure out the direction of the surface normal. We know we want it to point outward, but how do we know what is outward and what is inward? What I like to do is to take this object and blur it. Now we have a blurred version of the object, and then calculate the gradient of this. The gradient will always point inward. So we just make the surface normal in the opposite direction to the gradient. And this works very well. It can get a little bit confused if we have really fine features on the order of our blurring. But as long as we resolved it with enough resolution in our grid, that really shouldn't be a problem, and we can get all of the surface normals correct. Another quirk about SolidWorks is it likes to put the vertical direction being Y, and most people think of Z being the vertical direction. So a lot of times when I read an STL file in from MATLAB, I will immediately reorient it so that Z is the vertical direction. So here's the code for. Okay, now we're changing subject again. What we want to talk about is generating surface meshes, but very quickly I want to show you how to visualize the surface mesh. And we do that using the command patch. And so if we have our faces array and our vertices array, we just hand those to the command patch, and it will draw that object and return a handle to that. And then with this handle, we can set different properties. We can make it partially transparent. That's what this face alpha does. That makes the faces 50% transparent. The face color is blue. Notice the pyramid looks blue. We're making the edge color black. So the lines, the edges, will be drawn in black, and a line width of 2. So that's it. That's how we draw our surface meshes. Now on to the more important topic. If we build a device in MATLAB, how do we create this surface mesh? There's 2 ways we can do this. We can sort of directly generate the surface mesh, or a lot of times if we're modeling it with finite difference time domain, finite difference frequency domain, we've built something on a grid and we want to mesh that. So first, MATLAB does surfaces. And in this case, they're not triangles yet, they're squares. But we can store those in XYZ arrays. And you've done that when you've called the surf command. But essentially, this is what your array looks like. X and Y would contain the transverse positions of these points, and Z would contain their vertical height. So all of these, X, Y, and Z, are all 2D arrays because we have a surface, but it has an X position, a Y position, and a Z position. If we do that and then call the command surf, we might see something like this. So this particular surface has this as X, this as Y, and this as Z. So I suggest looking at these and compare it to that to kind of understand what's going on. So MATLAB has some neat commands for generating these types of surfaces. There's a cylinder command, there's a sphere command, and probably some others that I'm forgetting about. So let's generate a triangular surface mesh for a sphere. So first, we use the built-in MATLAB command sphere. And what it'll do, it'll create arrays that are 41 by 41 points, x, y, and z, that distribute all those points around the sphere. So if we were to hand these to the command surf, we would see a sphere. Well, remember this has square faces. So MATLAB has another nice command, surf to patch, which will take these squares, if you will, and convert them to faces and vertices. So we can use commands like cylinder, sphere, ellipsoid to generate some very primitive looking 3D objects, but with square facets, if you will, and then you surf the patch to convert that to triangular facets, and then we can save that as an STL file or do whatever we want with that. Another very common thing in MATLAB, at least particularly for the type of research we do, is we'll be modeling something three-dimensional in finite difference time domain, and we have some kind of three-dimensional object. Or maybe we've generated a three-dimensional spatially variant lattice, and it's distributed on a 3D grid. So here's a 3D egg, I guess, if you will. What we're after is the surface mesh. How on earth do we do that? Well, it's just one command in MATLAB. The first thing we do is we create the elliptical object, OBJ. So here, if we display OBJ in 3 dimensions, this is what it would look like. Then we use the command isosurface. We give it XYZ, which is really our 3D mesh grid for our coordinate axes. Then we give it our object, and we give it a value to form that isosurface. Well, up here we just have zeros and ones. If we give it a value of 0.5, it will place a surface right around the edge of this. And so what comes out are the faces and vertices of that egg-shaped object. So one line of code in MATLAB. That's pretty cool. Now let's think about this the other way around. What if we have surface mesh and we want to make that a 3D object on our grid? So in other words, we would be importing an STL file into MATLAB. How does that happen? And it turns out this is a bit more complicated. First, we need to talk about some math describing a plane. It probably is easiest to start with this equation. In general, we can describe a plane with these equations. With this equation, AX plus BY plus CZ plus D. Once we have a plane, we can define its surface normal, and it turns out it's not the surface normal, but the normal to the plane, in this case our facet normal. It will be AX plus BY plus CZ, and we want to make the magnitude of that equal to 1 so that this is a unit vector. That's the facet normal. So we see a very clear relation, and notice that D does not enter into the equation for the facet normal. We can write the equation for our plane in vector notation. S carries components A, B, and C, and notice we have AX plus BY plus CZ. This is a dot product between the facet normal and position. So it's S dot R plus D equals 0. So that's the vector equation for a plane, where R is position. Then if we know any point on that plane, then we can finally figure out what D is. So if R naught is the point on the plane, we can solve for D. But we have to know a point on the plane. So here's our equation for a plane. And that was a vector notation replacing AX plus BY plus CZ. We calculated D with this expression once we knew a point on the plane. Well, now we can factor out an S, and here is a useful equation for a plane. The surface normal dot product, position minus a known point on the plane. And as long as this position is such that this dot product ends up being 0, that is a point on our plane. Otherwise, it is not. And we need to use that information as it turns out. Now, given a position R sub I how do we know which side of that facet it occurs on? We know in an STL file the facet's pointing outward. We sure would like to know which is inside the object or outside the object. So, given some point r sub I, if this equation for the plane, so here's the actual equation for the plane, but if we calculate this for some r sub I and it's less than 0, then this point r sub I occurs on the opposite side that this facet normal is pointing to. If it equals 0, then we know we're on the plane. That's the definition of the plane. If this equation ends up giving us a positive number, that means this point r sub I is on the same side of the interface as the facet normal. So now we have a way of determining which side of that a point lies on. Okay, so here's our algorithm. Step 1, we need to determine the axis limit. So what we do is we read in our STL file and we look at all of the vertices and we figure out what's the absolute minimum numbers. That must be where our grid has to start. Let's look at the maximum numbers, and that has to be where the grid ends. So these are our extremes. We know that any point in that object has to occur within this range of values. Then we calculate our 3D grid stuff. So we need to know the size of the grid. Here we're choosing how many points to put on the grid. 32 is probably a low number, but good for this example. And then we create our axis arrays. Step 3, we need to know the center of the facets, and we also want to calculate the facet normals. So I create 2 arrays here. This first one stores the facet normals, and then the second one is the center of each facet. So we have a triangle. This is smack center of the triangle. And so I create a loop, and I loop through all of the facets. So little nf equals 1 to big NF, where NF is the number of facets. The first thing we'll do is figure out the vertices. So we go to the F array. This gives us the index of the first point in this facet. Once we know that index, then we can go to our vertex array, feed it that index for all 3, and we'll have the X, Y, and Z components of the vertex. And then we do it for the second vertex and the third vertex. So we pulled off our 3 vertices. We have 3 vectors, 3 vertices. Now we're going to compute the facet normal. Here we're depending on the cross product, here we're depending on the right-hand rule to give us the correct direction for the facet normal, and we're using the cross product consistent with that right-hand rule to give us the facet normal. So we calculate P1 and P2. These 2 vectors will point away from the vertex 1 toward vertex 2 and 3. So these 2 vectors then define the plane that that facet lies in. So if we take their cross product, now we have a vector normal to that plane, and then we want to normalize it to be unit amplitude, and we store that as our facet normal. Then the position, the center position, we just average the 3 vertices and we store that. So all we've done here is calculate the center of each triangle and all the facet normals. Now what we need to do, given that information, we're going to set up our 3-dimensional grid, and we're going to loop through that 1 point at a time. For each point, we're going to look through our list of facets, and we're going to find the closest one, and we're going to use the center position to do that. So we'll be looking at where the point is on the grid. We'll go through all those center positions of the facet. We'll find the closest one. Then we want to resolve which side of the facet that point lies on. And that's why we discussed the math behind planes. So we loaded an STL file, and maybe we want to build our object into ER for the permittivity. Well, we set up our triple loop over X, Y, and Z. We get the position of that point on the grid. Then we seek out the closest facet. And in the end will be the index of that facet that's closest to this point on the grid. Then we want to check if that's inside or outside the object. So really A is that dot product, and here we're setting it to be 0 if it's on the same side of the facet as the normal, which points away from the object, or it will be set to 1 if it's on the opposite side and actually inside the object. And so that's it. We loop through the grid and we fill in all the points. So what does this look like? Well, let's say we go into a CAD program and we build our pyramid. We import that into MATLAB and we use a command like patch that would draw it, and then we run the algorithm on the previous slide and we can fill in a 3D grid with that pyramid. Now we're ready to model this with something like finite difference time domain, finite difference frequency domain, rigorous coupled wave analysis, any number of things. And here's one I did just for fun. I found an STL file of a dinosaur, a velociraptor or something like that. I imported that into MATLAB, ran the exact same algorithm, and here's a velociraptor. So now we could model scattering from a velociraptor. That's essentially it for this lecture. I wanted to point on a couple other things that tie into this, and the first one is point clouds. Beware of online tutorials. I looked up some online tutorials of point clouds, and I did not find them very useful. A lot of them were old and outdated, so just beware of online tutorials. What is a point cloud? Well, on the left here may be our actual object. A point cloud is just a whole distribution of points on the surface. And if we have enough points spaced closely enough, we can kind of make out what that is. And where these point clouds come from mostly is 3D scanners. Maybe there's a laser doing circles around an object and it records the distance to the edge of that object, and we get this set of points. And there's CAD programs that can take these point clouds and turn them into CAD files. So here's just some examples. Upper left, that looks like a brain. Some other type of object on the right, and a car that's been scanned, the body of a car into a point cloud, and that could be imported into a CAD package. So how is the point cloud data stored? Well, it's just a whole list of points. So we'll create an array called PC for point cloud, and then the first row would be the XYZ position of the first point. Second row will be the XY position of the second point, and so on. And usually there's a large number of points. So that's what this array would look like, and it goes on very far. The more points you have, the more memory things will take, the slower it's going to take, but the better you can resolve that surface. So if we have all this point cloud data in MATLAB somehow, how do we save that? It turns out that's really easy. In fact, we can do it in one command. So PC will be our point cloud. I'll explain the order here in just a second. But we use the command DLM write, and this writes a delimited file. We give it the name of the file, .xyz, that's pretty standard extension for a point cloud. And we give it all the data for the points, and we make the delimiter a comma. Now, if we originally saved our points XYZ, this is how we would like to think about it, but then we read it into something like SolidWorks, it comes in lopsided. Remember, SolidWorks thinks that Y is the vertical direction for some reason that I've never learned yet. So if we want to bring this into something like SolidWorks, we just reorder the points and do something like X, Z, Y. Now when we read it in, we see our object. Now one other point, a program like SolidWorks, when it reads in a point cloud, it likes that first line to be X, Y, Z. And then it knows it's a point cloud and it knows how to interpret the data. So what we did on the previous slide did not include the X, Y, Z. So you can do one of two things here. I think the easiest is to open this up in something like Notepad and just add X, Y, Z. And of course, if you want more automation, you can write a more sophisticated text file saver, like we talked about at the beginning of this lecture, to put in the X, Y, Z automatically. Now, in SolidWorks, if we want to read in a point cloud, we have to do something. We have to activate that add-in. So we go into the add-ins and we want to make sure that the scan to 3D is checked off. And then we have that option. Then click OK. Then we want to open the point cloud, but when we open, it's initially just looking for SolidWorks files. So we want to say open, but then we go down and select the point cloud for the file type. And You notice you see XYZ for the extension. And so now, when we open it, that will let us read it in. Then we want to run the mesh prep wizard. That takes the point cloud and actually creates the mesh from that. So then we have an object. And the last thing I want to point out, if we have very sparse points, you know, SolidWorks does an okay job of generating the object from that. But notice as we go to more and more points, the object becomes resolved better and better. And so whether we're generating these points in MATLAB or whether it's a 3D scanner, we always get a better object in the end with more points. But it takes up more memory and is slower. While I use SolidWorks here, I would not say SolidWorks has a very good ability to mesh point clouds. Now, I don't know from personal experience, but I hear that Rhino 3D is an excellent program for taking a point cloud and generating a surface mesh. The other thing, even though we can create a surface mesh in SolidWorks, it's not really an editable object. But the purpose for that is that you bring in a point cloud and it kind of just stays there visually, and then you model something manually that fits the shape of that. Anyway, the whole procedure there I think is beyond the scope of this lecture, but suffice to say that when you mesh it in SolidWorks, it's not an editable object. It's really just there to serve as a template, and you sort of trace your model around it, if you will. Last subject here is importing a custom polygon into SolidWorks. So very often in electromagnetics, we design the shape of something and it's crazy, but we want to precisely place those points and then read it into SolidWorks and extrude that. For whatever reason, SolidWorks does not provide the ability to do that. It has one thing that kind of looks like that. A little spreadsheet pops up and lets you enter a whole bunch of different vertices, but it turns out it fits a spline to it, which is a smooth type of line. But if we really want those vertices fixed, at least up to the 2010 version of SolidWorks, we weren't able to do that. And I am a little bit out of date, and I probably need to check on that again. So anyway, let's say somehow we've modeled something and this particular crazy shape works wonderfully. But we need the positions of these vertices exactly. We don't want it interpolated or smooth. We need those positions perfect. We can pretty easily imagine where there's thousands of points and we don't want to type all those in manually. That I can find, there's no feature in SolidWorks to do that. So here was the workaround that I found. So here's where I was talking about, so be careful. Here's a little option where you can curve through XYZ points. A little spreadsheet pops up, you can type in numbers. However, notice I've typed in the positions that would essentially do a square, but when it draws it, it's an oval. It's really a spline, and it interpolates and it smooths, and it's not suitable for bringing in custom polygon. So the first thing we need to do in something like MATLAB is figure out the positions of all those vertices. So in MATLAB, we'll end up creating an array P, that contains the positions of all those vertices. So this first row will be the X, Y, Z position of the first vertex, X, Y, Z position of the second vertex, and so on. Now notice I set all the Z positions to 0. We're importing a polygon and it's flat. So we'll say that this cross section is the X and Y plane. It's flat in the Z direction. Once we have this array of data, we need to save this in some format that we can read into SolidWorks. And on the MathWorks website, there's a function that somebody wrote called IGESOut. And this save was called an IGES file. That is a CAD format. And all we do is we hand it that array of the points in our polygon, and we tell it to name that file poly. So what this function does then, it takes all your points and saves that in an IGES file called poly.igs. This is the file that we can load into something like SolidWorks. And SolidWorks is the example here. So our next step is to load it into SolidWorks. We go into SolidWorks, we say File Open. We definitely have to scroll down and select the IGES file type. Then we also want to click on Options. Now, one of the options, here's what we need to do. 3 important things. The first one is we want to make sure that this surface solid entities is unchecked. We're not importing a solid body, we're importing just a polygon. This needs to come in as a sketch. The next thing we want to do is check the free point curve entities, and then also make sure the radio button is import as sketches. We're importing our polygon as a sketch so that then we can extrude it and do whatever we want to it. At this point, we can open the file. Now that it's in, it brings it in as a sketch, and we can do whatever we want to it. We can extrude it, we can revolve it, we can do all kinds of crazy things. So this was my workaround for importing a custom polygon into SolidWorks. And that's the end of this lecture.